Welcome to our discussion on Way ANOVA. In previous lessons, we looked at ways of comparing the means from two independent samples, right? Two different samples. Now, we're going to look at a way to test the equality of three or more means by using a one-way analysis of variance called an ANOVA. So really all we're doing here is we're expanding a two-sample t-test to a multiple sample. But it's no longer a t-test. It's going to use an F distribution. The F distribution, as we've seen before, is not symmetric. It's skewed to the right. Values can't be negative, right? They're always 0 and above. And the exact shape of it always depends on the two different degrees of freedom. So if you don't remember, this is basically what it looks like. It looks very similar to the chi-square distribution. When we're doing a one-way ANOVA, we're testing the hypothesis that three or more population means are all equal. And because the calculations are extremely complicated, we're really just going to use a technology and look at how to get answers out of technology. Just like before, small p-values, right, mean that we're going to reject the null hypothesis, and a large p-value means we fail to reject. So let's look at the basics of a one-way ANOVA. A one-way analysis of variance, or a one-way ANOVA, is testing three or more population means by analyzing sample variances. A one-way analysis of variances is used with data that is categorized with one treatment, one factor, which is a characteristic that allows us to distinguish the different populations from one another. So the idea is each of these populations, right, you're going to have a sample with a mean, a sample with a mean, and a sample with a mean, and they are all coming from populations that are different because of one thing, right? They only have one different characteristic. They might have more than one, but you're only testing them based on that difference. They're in group A because they have a little of this amount, right? Group B because they have more of it. Group C because they all have all of it. It could be something as simple as testing for the average IQ of Democrats, Republicans, Independent, Green Party, Tea Party, no affiliation, right? Obviously, people that are in each of those populations can differ on other factors, but the only factor that we're using as kind of the grouping factor, the reason why they're in one group versus the other, is their political party affiliation. Okay? Later on, we'll look at how we can look at data that's categorized two ways, and that will be the two-way ANOVA. With the one-way ANOVA, our requirements are that the populations have approximately normal distributions. So you should be doing your histograms and your normal quantile plots and different things to test that your samples come from normally distributed populations. The populations have the same variance or standard deviation. The samples are simple random samples of quantitative data. The samples are independent of each other. And the different samples are from populations that are categorized in this one way only, right? We're only breaking them up into groups based on one category or one characteristic. In order to test your null hypothesis that all of the means are the same, you're going to want to use technology. The TI-83s can do these, StatCrunch can do it, all the more advanced things like SAS and SPSS. You're going to want to identify your p-value and then use that to reject rather than trying to come up with critical values. When we conclude that there is sufficient evidence to reject the claim of equal means, we cannot, however, determine which of the means is different from the others. You have to use separate tests to do that. The one-way ANOVA just tells us whether or not at least one mean is different from all of the others. We don't know if it's 1 is different or 2 is different or 3 is different, and we don't know which one is different. We just know that there is at least one that stands out from the pack. We'll see in part 2, we'll discuss briefly some of the ways that we can actually then delve deeper and figure out which of the means are in fact different. Here's a simple example. We have IQ scores and we're going to use a significance level of 0.05 to test the claim that these three samples come from populations with means that are all the same. And if you look at the descriptions, right, one sample comes from people who had a low level of lead in their blood. The other sample were people who tested on a medium level of lead in their blood, and the third one has a high level of lead in their blood. It's a commonly held belief that lead leads to lower IQ scores. It's one of the reasons why we've taken lead out of paint for well, for everything, but it started off with taking it out of paint that were on toys because we were afraid kids would chew on it and get lead in their system, and then it would hinder their mental development. Here are the summary statistics from those three sets. Basically all you're doing is running simple summary stats on each of the three samples. You get your sample size n, right, your x bar, which is just the mean of your sample, and then s, the standard deviation of your sample. You would also need to check that all three of them come from approximately normal populations, so you would run your normal quantile tests or histograms or something and see that they're all approximately normal, and then check for outliers. And in one of the samples there were some potential outliers, and the others not so much. Now that you have that, you run through the requirements and go, yep, everything seems good. We can go ahead and run our test. Our hypotheses, right, our null is that the means are all the same. The alternative is that at least one of them is different. We're going to let alpha be 0.05. And of course we're doing an F distribution, so our test statistic is going to be an F. Here's what we'd get out of StatDisk. You can see the test statistic is here at 4.07. P-value is there. If we did it in Excel, which is relatively easy to do, there's your F value. There's your p-value. They also give you the f-criticals, right, but you don't really need them. They give you a bunch of other stuff that we don't need to worry about either. In Minitab, there's your f and p, right? And then in StatCrunch, there's the f and p. Very easy. If you ran it in your TI calculator, here's your f statistic, there's your p-value. So as we can see, technology is very easy to read the displays. Let's see how easy it is to actually get it to run it for us. We're going to look at how to do it in StatCrunch. In order to do it in StatCrunch, there's one of two ways. Either you have to put your groups, so in this case we had three groups, we'd have to put the three groups in three different columns, or you can put all of the data in one column, and then you have to have a grouping column, right? So this first column is the lead column, which just has ones, twos, and threes. You'll see that as we scroll down, now all of a sudden there's some twos. This means they're in the second group, the kind of middle of the road lead levels, right? The first group was low lead, this is medium lead, and then 3 means high lead group, and these are the scores of all the people in that group. So you could either put those in 3 different columns or put them all in one with a grouping column. Either way, it's just as easy to run. In here you go to Stat ANOVA, a one-way ANOVA, and then because we're doing values in a single column, we select right responses are the IQs, the factor, that's the grouping one, is the lead column, compute, and there is the exact same answer that we got before. There's the F and there's the p-value, along with all the extra stuff. It's also kind of nice, it gives you the descriptives. So here's the mean, standard deviation, etc. for the 3 groups, which would help you determine which of the 3 was different. Right, we're just testing for a difference, and right here it's pretty obvious that group 1 is the difference. 2 and 3 are identical, more or less. So it looks like the low lead group has a statistically significantly higher average IQ than the medium and high lead groups. Okay? Very simple. Because our p-value was, in this case they rounded to 0.02, and it's less than the significance level, as we can see that there is sufficient evidence to reject that null, which means there is significant evidence to show that the three means something is different amongst them. Why this works, this is just talking about how how we're measuring these things. It's looking at the variation between the samples based on and then in relationship to variation within the samples. So sample variances and then variance amongst the three means, and that's how the F statistic works. If you get sample means that are very close, you get a very small F, and that's gives you a very large p-value, and then therefore you fail to reject. And conversely in the other direction, because the F statistic is very simply just a ratio of the variance between the samples divided by the variance within the samples. And variance within the samples just means the variance of that sample, right? Standard deviation squared for each sample. Be careful. When we're testing for the equality of three or more populations, we have to use ANOVA. We cannot simply just run our regular two-sample t-tests over and over and over again, right? You might think, well, hey, there's three groups, so can't I just test a difference between A and B, a difference between A and C, and a difference between B and C? I'll just run three two-sample t-tests. The problem with that is you're not controlling for your alpha level, right? Your alpha of 0.05, if you do it 3 times, right, just simple math tells you that if you're setting alpha to be 0.05 and you run this test 3 times, that means you're 95% confident for each test, but you're now running 3 tests. So you're only 95% confident for each of those 3 tests, which means combined you're only 0.95 cubed, or 0.8574, so a little less than 86% confident. Now your alpha level just shot up from 5% to 14% because you did 3 t-tests instead of 1 ANOVA. So what an ANOVA does is it allows us to test all those things all at once, and we can therefore maintain our alpha level. Okay, we said that there are some ways to then identify which of the means are different once we found that there is a difference. There are detailed discussions on the calculations and ramifications of sample sizes and things like that that you can look at online. We're not going to have time to go into that. Just know that these can get quite complicated. When performing an ANOVA, we have to use one factor as the reason why we're going to partition our data into these several categories. And then if the test comes back and we're able to conclude that there is a significant difference among those means, we don't know where the differences occur. One way to kind of reduce the effect of possible extraneous factors is to run a completely randomized design, which means each sample value is given the same chance of belonging to the different factor groups. And that would only work if you were actually you couldn't put someone in one of the 3 lead groups. They have self-determined where they're going to go based on the level of lead in their blood. It's not like you can go around and go, okay, here, you eat a bunch of lead, you eat a little lead, you don't eat any lead at all, and then now I've randomly chosen who goes into which group, right? You can only do the completely randomized design with a factor that you actually have control over. So in most cases, you unfortunately can't do that. Another way to reduce the effect of extraneous factors is to use a rigorously controlled design, and what that means is sample values are carefully chosen so that all other factors have no variability. So this would go back to the lead stuff where you have a bunch of patient files, right, and you have taken them and put them in 3 groups based on their blood lead levels. And now you look at those 3 groups and say, how can we make them as homogeneous as possible? So let's maybe we think gender has something to do with IQ. I know it doesn't, but if you did, you'd go, okay, then let's look at just one gender. And then you go, okay, maybe race has something to do with it. So then you only look at a certain race from each of those three groups. And then you look at maybe you think, I don't know, diet has something to do with it. So you can see how you would then pick and choose randomly. You would take everything in your group that had the certain characteristics you were looking for and then randomly choose from those that were left over from each of the three groups. And now your three groups are relatively similar on all other factors besides lead levels. You're controlling for other possible factors is what you're doing. After you've done that and you want to try and identify which means are different, you can construct box plots of the three samples and see how they relate. The best thing to do is if you can construct all of the box plots in one graph so you can see how they overlap or not. You can also construct confidence intervals around their means and again look for those that overlap and those that don't, because if there's one that doesn't overlap with any of the others, then that's the one that's different. You can also look at other types of tests, range tests, multiple comparisons tests, and then the more kind of commonly used one is either the Bonferroni or the student t-test. Those are the two that are normally run as an extra test on top of an ANOVA. This is the calculation for the Bonferroni. Don't worry about it. Technology is going to do it for you. If we go back to our example with our IQ test scores, our initial null hypothesis was that they're all the same, and here we just wrote it in pairs because that's kind of what the Bonferroni is now doing, is it's going how are each of the pairs looking. Here are the numbers that we calculated for sample 1 and 2. And if we compare that, we get a t of 2.252. If we do the same thing for all the others, we can get the p-values for each. And then here's the summary of all of them that you would get out of, in this case, SPSS. What you're concerned with or what you're looking for are the significance levels. Right? Here is your significance level when you're testing 1 versus 2, and here's the significance level when you're testing 1 versus 3. You can see that when you test 2 versus 1, you get the same thing. Duh, right? It makes sense because 2 versus 1 is the same thing as 1 versus 2. And then 3 versus 1 is also the same here. Now 2 versus 3, you'll notice in both cases has a 1. These are p-values, remember? And so this is a probability of 1. And if you remember from those two, 2 and 3, they had almost identical means. That's why you get a p-value of 1, because they're almost identical. But from looking at the tests of 1 to 2, 1 to 3, you can see that none of them are significant at a 0.05 level, right? So it depends on where you want to set your level as to which one you would say was actually statistically significant. So in this particular case, we have kind of the rare result where the ANOVA comes back and gives us a significant result, but when we look at the pairs, we don't actually get a significant result for either of the pairs. So none of them are actually significantly different from the others as a pair, but as a whole, they were off by enough to trigger the ANOVA. And so our conclusion would be, even though the ANOVA test tells us that at least one of the sample means is different from the others, the after test, right, the Bonferroni or Bonferroni, however you want to pronounce it, test results in it's not able to identify any one particular sample mean that's significantly different from the others, at least not at an alpha level of 0.05. 1 versus 2 was very close at 0.08, and 1 versus 3 was a little worse at 0.09, both of which would be significant if we tested at a 0.1, right, alpha of 10%, but at 0.05 neither works. Now, as far as technology is concerned, if we had run our ANOVA like we did last time, all we have to do is tick a box at the bottom. So our responses are the IQP. lead, right, is the factor. And then down here, Tukey, you're going to run a Tukey test. I think I misspoke earlier and said in addition to Bonferroni, there's a student t-test. I misspoke. It's the Tukey test is the other more common test for, you're basically checking those two pairs, right, pairwise differences. If we run this, we get the same normal results we got last time. It shows the descriptives of the three groups. It gives us our overall ANOVA decision, right, of rejecting the null. So we're seeing that there is a difference. But then we come down here and we're testing, I left it at 95%, right, because we were testing an alpha of 0.05. We can see that when we test 1 versus 2, that's what this means, right? 1 subtracted from 2. So group 1 versus group 2, we get a p-value of 0.0667. The thing that we had from the other technology was 0.079. I might have a slightly different set of data. And then 1 versus 3 gave us 0.0758. And then 2 versus 3, right, gave us that p-value that was basically 1 that we got from the other one, because those two, 2 and 3, as you can see up here, are almost identical, right? Same results. We get a statistically significant ANOVA with the p-value of 0.0195, but none of our pairwise results are significant. Okay, so very simple in technology. That's how we run a one-way ANOVA with a Tukey test to check for the pairwise differences.